Thank you for tuning in to hear my talk today. I'm excited to share with you work that we have done over several years to add a problem-based learning experience to our unit operations lab at Brigham Young University. Anyone who has done any research into pedagogy knows that problem-based learning is an effective teaching strategy that requires students to access high-level critical thinking skills and accomplish tasks similar to what is found in professional engineering practice. Despite these advantages, implementation of PBL in typical engineering curricula is often difficult due to cost, time, and space limitations. And these complications can be exacerbated by increasing enrollments experienced by many engineering programs. Because of these difficulties, our department shied away from implementing PBL in our curriculum for many years. But then assessments began showing something disturbing. Our students started having less problem-solving and critical thinking abilities than we desired. And this is something that colleagues at several institutions have told me they also see. I can't find any hard studies, but I personally think the change came from the internet. The internet, with its search algorithms and easy access to any procedural knowledge, does a lot of critical thinking for you. Before Google, engineering students practice a lot of critical thinking by developing their own tricks of the trade to find information, simplify numerical problems to be tractable, developing their own hacks to solving problems, and so on. The internet now does all this for you, or shows you a video where others have done it, so little thinking is required. This isn't necessarily bad because it means we should be able to move students further along the path to becoming competent engineers and not get bogged down in as many mundane tasks. But it means that we need to change our pedagogy to ensure that we still require the mental calisthenics needed to develop critical thinking skills. So how does this lack of development in critical thinking manifest itself? Well, I noticed it because I teach unit operations lab. A big part of our lab, which I'm sure is like yours, is that we try to present our students with a design problem that they can solve by doing some experiments on pilot or benchtop apparatus and then scaling up to the industrial size. We try to be as open-ended as possible, but because the equipment is already set up, they are limited in what they can really change in the process. Now, you and I know that even within this limitation of having students run existing equipment, that a lot of engineering can be done to understand and optimize the process. In fact, this is very similar to what many BS chemical engineers do for a career. And for many years, our students seem to get this and own the processes. But something changed about a decade ago. Students stopped digging in and trying to really understand the process. If we told them to take pressure drop versus flow rate data for this non-Newtonian fluid, fit it to a power law model, and then use this to get a friction factor and design a pump system, they could do it. But a decade ago, we didn't have to give such detailed instructions, and students still figured it out. The sentiment from students can be summarized with these two comments. The requirements for the labs are too vague, but the experiments are too canned. Students wanted more open-ended problems, but they also wanted to be told exactly what to do. A key part of PBL in a university course is the open-endedness of the problem being solved. Predisposing the students to a particular approach should be limited or eliminated. Moreover, students should not have learned all the technical material needed to achieve the aims of the problem, but should be required to learn new skills and acquire new knowledge without prompting from the instructor, and often only after realizing this need after initial failure. To this end, we constructed the following problem statement for the students. Your task is to design, build, and validate a flow system where water is taken from a tank, passes through the shell side of a heat exchanger, and then returns to the tank. Your system must have at least 30 feet of pipe after the pump, and you must be able to control the system and achieve any flow rate between 1 and 9 gallons per minute. Cost should be as low as possible, and the apparatus must fit inside the specified location in the lab. I recognize that some specificity is included in this problem statement, including 1 to 9 gallons per minute and 45 feet of pipe. Strictly speaking, such runs counter to the idea of problem-based learning, and it would be better to start with a broader problem, such as the plant needs to heat 100 gallons per minute of reactant A from 70 degrees F to 100 degrees F, but compromises were made to fit the experience into the university setting, where money, time, and space are limited. But notice what is not included. What size pipes should be used? What size pumps should be used? How will I measure and validate the flow rate? How do I measure costs? How do these include both capital and operating costs? If this is a heat exchanger, should thermocouples be placed in a line? Where will the tank be located? Where will the pump be located? Where will the pipes be located? How will I control the system? How will I make it safe? As is apparent from this list, some choices regarding the motivation behind the problem have been made, and arbitrary lengths and flow rates have been selected and changed from semester to semester. But students must make many decisions about the project from its initial inception to its conclusion. So what resources are given to students? Here is a picture of the space where the projects are built. Students construct their apparatus in one of the 4 areas outlined by striped hazard tape. In general, teams of 4 students work on each project, thus 16 at a time may be accommodated with this setup. The room is approximately 460 square feet and each construction area is approximately 55 square feet. Also shown in this figure are the electrical connections which power the pump for each project and the conduit through which students connect the control system to the motor starters. For safety, students never interact with high voltage AC power. The motor starters, which are high voltage, are found in the blue room pictured in the background. Students don't have access to this room. Rather, the students construct a control system which sends a low voltage DC signal to the motor starter, which then sends the AC power to a mechanical interlock switch. The pump plugs into the switch, which is composed of 2 levers, both of which must be engaged to supply power to the pump. In short, students never interact with high voltage AC power. All their wiring and connections are only DC power with a max of 24 volts. The high voltage AC power can be immediately turned off by physical as well as software means. Students are provided with a variety of equipment to fulfill their design requirements, including different powered pumps from 1/3 to 2 horsepower, Schedule 40 galvanized steel pipe in lengths from 1 inch to 6 feet and nominal diameters from 1/2 inch to 1/4 inch, various fittings, differential pressure transducers, and the list goes on and on. Students are free to use these supplies in any manner they desire to fulfill the design conditions. The big decisions they need to make are the size of the pipe to use, the size of the pump to use, and the layout of the pipes. Our UL Lab class meets twice a week in 2 3-hour blocks. A semester consists of 28 class days, and the PBL experiment takes 12 of the 28. Approximately 4 of the 12 are devoted to preparation and planning the project. 5.5 days are for building, testing, rebuilding, 2 days for writing, and about half a day for dismantling. So let's get to an example of a student project. Remember that the apparatus had to have 30 feet of pipe and control the flow rate between 1 and 9 gallons per minute. The main part of the proposal is developing a system demand curve and overlaying this onto a pump performance curve. This plot is head versus flow rate. These students showed system curves for building with 3/4 inch and 1 inch pipe. 2 pumps, 1/3 horsepower and 1/2 horsepower were shown here. The dashed vertical line is the required flow rate. Based on these calculations, the students chose to construct their system using 1 inch pipe and a 1/3 horsepower pump. Here is a picture of the apparatus built by the students. Notice that the pump is plugged into the pump interlock on the wall. Also notice that the wire carrying the signal to the motor starter. This line originates from the NI control modules and ends in the junction box. The junction box has a connection to a permanent line that travels up the wall, through the ceiling, and into the blue room shown earlier. Notice that the students also put pressure gauges around the heat exchanger. Not all students do this, but it's useful to redesign the system if needed. As shown on the previous slide, students size their pump using the mechanical energy balance, which appropriate major and minor losses. All the minor losses coefficients are readily available in the literature except the losses across the exchanger. Students estimate this loss, but after building the system, their estimate is usually incorrect, and they have either over or underbuilt the system. Overbuilding results in flow rates that greatly exceed the design specifications and an apparatus that is excessively expensive. Underbuilding yields an apparatus incapable of meeting the specified flow rates. The better students realize this and design the system with a measurement device to improve their system demand curve. Let's look at this design experiment redesign process because it's such an integral part of the PBL nature of the experience. Recall that the design requirement included the ability to control the system between 1 and 9 gallons per minute. To demonstrate this, the students, once the flow meter was properly calibrated, performed experiments where they determined the flow rate as a function of the percent of the valve opening. Their data are depicted here. You will notice, like the students did, that the globe valve does not provide much control unless the valve is closed more than 50%. This is another PBL moment. The students recognized that such was not optimal and considered how to change this. They had to learn the features of desirable control and found that the control valve should account for approximately 50% of the losses in the system to be most effective. But more to the point of the design conditions, the students realized that they had likely over-designed their system since they were able to achieve flow rates about 44% higher than needed. Remember, they had to assume a loss constant for the heat exchanger. They assumed a value of 50 for their initial design. When they calculated a new value from their experimental pressure drop data, they found a value of 4. Using this new value, they recalculated the demand curves required by the system as seen here. Notice that with a more accurate K value, a system consisting of 3/4 inch pipe can meet the design requirements with a 1/3 horsepower pump, whereas the initial estimates indicated that such a setup would not achieve the required flow rates. The students did not have time to reconstruct the system using only 3/4 inch pipe, but they provided a cost comparison as seen here. This analysis included both capital and operating costs. Since both systems used the same size pump, the operating costs were the same in each case. However, the capital costs were reduced almost 50% by using 3/4 inch pipe versus 1-inch pipe. I hope you see the big picture here. It's not that students designed and built a flow system. It's that they had a real problem-solving experience with enough options that multiple decisions had to be made that affected the ultimate outcome of the project in a measurable way. They made mistakes, recognized the need to learn new skills, and made correction as time allowed. And students love it. I have done repeated survey assessments on the efficacy of the PBL lab experience. These have been done immediately after the class, one semester after taking the class, and after graduation once former students have experienced real engineering practice. For conciseness, only a small fraction of the results are presented. The first data I will show you is in response to this question. The surveys were taken at 2 times. The first was immediately after the class, and the second was after students had graduated and had experience in the real world. The main point of the question was whether PBL should be kept in the curriculum or should it be replaced with a traditional lab like the others in the class. The respondents gave answers on a Likert scale. Here are the results. Notice that 85 total people responded to the survey given just after the course finished, and 57 graduates participated in the follow-up survey. The results are clear that students, both during the class and after gaining professional experience, feel that PBL should be kept in the curriculum. Here is the next question. Students were asked to select the lab from which they learned the most. This covered 6 labs done over 2 semesters. And here are the results shown as percentages. The results clearly indicate that students, both during the class and after gaining professional experience, feel that PBL was the best learning experience. In the survey conducted just after the course, 70% said they learned the most from PBL, with the next highest lab being 13%. And even with the advantage of experience in the real world, the trend continued with 54% selecting PBL, with the next highest being the fluids lab at 16%. The surveys allowed the takers to comment on the reasons for the ratings given. Select comments from both the after course and after experience cohorts are shown here. The sentiments are almost universally positive, and many of the comments express that PBL was the best lab in the course. A few even explain how it was the best experience in the entire curriculum. So how much did it cost to get this going? Renovating the room was about $120K, but that was about 8 years ago, so it might be double that now with construction cost increases. The equipment was about $100K, and you could still likely do that part for this amount. Finally, our lab manager estimates it took him about 3 man-hour months to design, build, and test everything. I hope you can see how we have successfully implemented a problem-based learning experience within the constraints of a typical unit operations laboratory in chemical engineering. The experience requires students to construct a system to achieve certain design requirements. Students plan the approach, physically construct the system using pilot scale equipment, test the apparatus, and assess problems. In doing so, they are required to relearn old material and learn new skills. The student projects are impressive, and the survey data of both students and alumni show that the experience is almost universally positive. The 460 square foot room can accommodate 32 students a semester, and we will expand to 92 students a semester this summer with new renovations. 2 other labs can still be done in a typical semester. Taken as a whole, our experience shows that PBL can be done with moderate costs and greatly improves student learning and problem-solving skills.